Hello, my name is Matthew Berg. I'm from Kansas State University, and today I'll talk about aerosol characterization with digital holography. So in our research program, we're interested in studying aerosol particles, and in many cases, when you want to observe these particles, you have to do so in a contact-free manner. That may be because the particles are inaccessible, or they're ice particles in the atmosphere, for example, that would melt if you tried to collect them. And regardless of the reason, light scattering methods tend to be a very good option to characterize these particles. And the gist of light scattering here for this application is you'd have some unknown particle and you illuminate it with a laser beam. It scatters that incident light off into all directions. And then you can take a detector and scan it around an angle and collect that scattered light. This gives you what we would call a light scattering intensity pattern. And the idea is that if you properly interpret such patterns, you may be able to gain useful information about the particle's physical form, such as its size, its shape, and possibly even its composition. But there's a problem with traditional light scattering methods of that form, and it's the inverse problem. And to give you an idea of what's involved there, suppose you measure a light scattering pattern that looks like this, the concentric green rings. Well, if you know a little bit about diffraction and basic scattering, you might expect that this is a spherical particle that was observed, and indeed in this case it is. However, what if you measure a pattern that looks like this? Very complicated. There's essentially no known way to invert this distribution of scattered intensity to retrieve the particle shape or size or refractive index. Fortunately, there is an alternative, and that is an imaging technique, digital holography. The basic idea with digital holography involves two measurement steps. The first, there's no particle present. You just have an expanded laser beam incident on a two-dimensional image sensor array, or CCD CMOS array. And you record a profile on that sensor of the beam. So we get something that looks like a big bell curve or Gaussian beam profile here. Here's an actual image on that sensor. We call this the reference measurement. Then we allow a particle, an aerosol particle, to show up in front of the sensor somewhere, and we repeat the exact same measurement. Now notice there's two waves present at the sensor now. There's the scattered wave due to the particle, and then there's the incident wave that was there before. The two interfere, and you get a system of interference fringes on your detector. Then lastly, what you do is take the difference of the no particle measurement, the first one, with the particle present measurement to assemble what we call a contrast hologram. And the purpose of doing this subtraction is you basically eliminate things like these rings here, which are either dust on the optics or multiple reflections from the optics. Now, to get an image from that interference pattern, we use the Fresnel-Kirchhoff diffraction integral. And the idea is this plane right here represents the pixel gray level readouts of the image sensor generated by the interference of the scattered and incident wave from the particle at the sensor. And then we just use diffraction theory to simulate the process of re-illuminating this hologram with a plane wave, although we don't actually do that in physical sense. We can do it here computationally with this Fresnel-Kirchhoff diffraction integral. The result is a complex function in two dimensions along x and y axes shown here that if you take the absolute value of it, you get essentially a grayscale image of the particle that was observed during the measurements. A while back, we did a proof of concept experiment to test how well this would work on moving aerosol particles. And you could ignore a lot of the optics here. Basically, we have a pulsed YAG laser, and we have an aerosol nozzle that delivers aerosol particles to a sensing region. To know when a particle was present, we have a cross-beam optical trigger, two beams of different wavelength. And so when a particle shows up at the intersection of these two beams, it would scatter both colors of light simultaneously. Those two beams are being shown here. So right there is where the particle is. And then we have PMT sensors monitoring the scattering region, and they can only see one color or the other of the trigger beams. And so if they see both colors at the same time, we know a particle's right at this intersection, fire a pulse from the YAG laser, and then we collect the interference pattern of the scattered and unscattered light across the CCD sensor here and get a hologram. Here's an example of the contrast hologram from ragweed particles. And if we, I'll just note that this is about as complicated as the light scattering pattern itself would be from such particles. But anyways, if we drop this in the Fresnel-Kirchhoff diffraction integral, we generate a nice silhouette-like image of the cluster of ragweed particles that were present during that measurement. You can see the individual particle grains here too. This particular measurement was actually done where the particles were on a microscope slide so that we could then transfer it over to an optical microscope, find the same cluster of pollen grains to verify that the holographic image was indeed faithfully reconstructing an image of the actual particle cluster. But this works just as well in the free-flowing aerosol form I was discussing earlier. And we find in general, after some optimization of the arrangement and other techniques, we can get resolutions in these images down to a couple of microns, although we have not achieved 1 micron resolution yet, which is an objective. We can also look at large numbers of moving particles. This was a fairly recent experiment, fairly simple. Again, we have a pulse laser, and this time it's sending out just a continuous, or not continuous, but a steady sequence of laser pulses. And the beam gets collimated and it goes through basically a plastic box that has a sieve on the top. And then we put some dust particles on top of the sieve and let the particles fall through into the box, through the beam. And when they do, if a pulse of light happens to be present, again, we get a nice hologram on the sensor, except now we can run the sensor at some, frame rate, I think about 30 frames per second or so. And in that sense, we can get a holographic movie. We can see these particles as they're passing through the beam and see how they move through it. Down here is just showing you some of the dust particle shapes. They're fairly big in this case. Applying the Fresnel-Kirchhoff diffraction integral to each hologram frame in the movie, the sequence of frames that is, we can run the reconstruction algorithm through the 3-dimensional volume of that plastic box. And each time this reconstruction plane, where the Fresnel-Kirchhoff diffraction integral is evaluated, is located at the location of a particle, then the image comes into focus. If it's not in focus, we get these dim gray lines that are basically a blurring aspect of the particle image as we go away from the good focus plane. But we can use that blurring aspect, which I'm showing here. So in layer 6, we have a particle that's in good focus. And then as we go to layers that are closer to the hologram and other layers over here, which are farther away from the hologram, we see that it blurs out. And we can define a threshold of gray value that lets us draw a contour around the blurred particle images. And then from that, we can construct sort of a hole, a skeleton for the particle. And by doing a calibration procedure, we can shrink this hole down and find a 3-dimensional representation of each of those dust particle grains flowing through the beam. And this just gives you an idea of what that looks like. Here you can see the movie of the particles falling through the beam. Well, so this is all about how we can get images of moving aerosol particles with holography. But that's not all you would want to do necessarily in an experiment or measurement. In fact, you may want to measure the light scattering pattern, the thing I was talking about at the beginning, because it does have useful information. It's probably the most direct way to get to a determination of particle material. But perhaps more importantly, for practical aspects, or atmospheric science aspects rather, It has particular radiative importance in atmospheric studies, such as how much sunlight do these particles scatter back into space when they're in the atmosphere, how much might they absorb, etc. And so it'd be nice to develop a method where we can both image these free-flowing aerosol particles and measure the light scattering patterns. And an early way we figured out how to do this was as follows. You can see here, again, I've got an aerosol stream coming out of a nozzle and another cross-beam trigger system so that I know when particles are present. This trigger event, obtained in the same way as before with PMT tubes seeing one color or the other of the trigger beams, will activate a red diode laser, send out a pulse, comes down, here's where the particle shows up from the nozzle, illuminates the moving particle, and we get a hologram with red laser light here on the sensor. This, by the way, is just a picture of a lot of particles going through those two trigger beams, just to give you an idea of scale here. Okay, but then we can add another laser on top of this at the same time to measure the light scattering pattern. And so this is being done in green light, again, a green pulsed laser. It's activated by the same trigger signal from the crossbeam trigger. And the way we achieve simultaneous measurement of the scattering pattern is as follows. So again, here is the particle showing up. And in red light, we have the hologram. Well, notice this element, this optical element here. This is a dichroic filter, specially coated so that it will pass red light, but it will reflect the green light. So the green pulse shows up and illuminates the particle, and its scattered light and unscattered light go off just like the red light does in the forward direction, which is down here. But it gets reflected by this dichroic filter. That's then intercepted by this lens. And the distance from this lens via reflection from the filter back to the particle is the same as the lens's focal length. So unscattered light, which is much brighter than the scattered light from the particle, being shown here in solid line, gets then focused down to a waist at the back focal plane of this lens. Meanwhile, scattered light, which is diverging away from the particle, gets collimated by that same lens. Here we have a mirror with a small 500 micron diameter hole drilled at a 45-degree angle through the mirror, and the focused, intense, unscattered light passes through that hole, leaving only the scattering pattern, it's been collimated again, to reflect off the mirror, gets relayed around through a spatial filter to get rid of noise, comes up over here, and then gets focused down to, or gets imaged down, relayed down to the sensor by reflecting off the backside of that same dichroic filter. And now the sensor is a color sensor instead of the monochrome sensors earlier. And so in the red channel of the color sensor, we get the digital hologram. In the green channel, we get the light scattering pattern. Here's an example of what that looks like. Here are two glass spherical particles coming out of the nozzle in aerosol form. This image is obtained from the red hologram that was measured. And then down here, I'm showing you the two-dimensional light scattering intensity pattern of these very same particles in this particular orientation. Over here, we've got a pecan pollen grain, and again, another one of its light scattering pattern for the particle in that orientation. Well, we can take this idea and realize that we don't actually have to measure the light scattering pattern if our particles are large. And the idea is the following. Our hologram, after applying the Fresnel-Kirchhoff diffraction integral, gives us a silhouette-like image of the particle. Well, then we can just take that silhouette-like image, apply the Huygens principle to it, and simulate the light scattering via some analogy to diffraction, in that if the particle is large enough, its forward scattering pattern will closely resemble its diffraction pattern. In this case, then, we just take the Fresnel-Kirchhoff diffraction integral again here for this later step, and instead of installing the contrast hologram in the integrand, we put the aperture function representing the binarized silhouette of the particle obtained from the hologram. So to test this, what we did is, here again are some of the particles I showed you before, the binarized silhouettes obtained from reconstructing the hologram, the actual measured light scattering patterns in the second row. So here's the two bispheres, or the biospheres, the two spherical particles, that is, the pollen grain and titanium dioxide particle, and here's a ragweed cluster. All of these are free-flowing aerosol particles. And then now, forgetting that we had the light scattering pattern measured, we take just these silhouettes and drop them into the Fresnel-Kirchhoff diffraction integral, basically apply Huygens principle. And now we can come up with a simulated or approximated forward scattering pattern from these silhouettes only. And you can see by comparing the measured light scattering patterns to the ones retrieved from Huygens principle, we do a pretty good job in each case, except for this ragweed pollen cluster, which I believe had too many fine scale structures, that the idea that the forward scattering pattern and the Huygens forward diffraction be the same is not particularly valid in this case. Okay, well, then the last thing I wanted to discuss is how we've applied some of these concepts to look at particles in the outdoor environment, outside the laboratory, in the field. In particular, we wanted to study the morphology of large atmospheric particles, say, the pollen particles I've mentioned, or dust particles. And so we developed a drone-mounted instrument to do this. We call it the Holographic Aerosol Particle Imager, or HAPI. And it flies on this DJI drone. Just to give you some quick specifications, the drone can lift about 5 kilograms, fly for about 15 minutes. Its ceiling is about 2 kilometers, although we never went that high, and we never moved it as fast as 65 kilometers per hour. But it was a very good drone for this application. Although I want to emphasize the payload is pretty limited. That meant that we couldn't construct the instrument. Here I'm showing you a schematic of the instrument HAPI out of laboratory grade steel and aluminum lens holders and lens mounts, filter mounts, etc. We had to use much lighter material. And the solution we came up with is designing parts and 3D printing them out of polymer in most cases. And that ended up working well, and we had an instrument that was light enough to fly on the drone. So in the instrument, you basically have 3 segments. You have a top segment here where the sensor and lasers are housed. You have this middle portion, which is pretty much an open, free channel. And then you've got this lower portion where some optics are. I'll discuss them in a minute. This thing hangs from the drone. And as the drone flies around, there's a flow of air laden with aerosol particles that pass through this channel. Now, if we focus on the red light over here at the left, what's going on is we have a diode laser that gets passed through an Axicon lens and then fanned out into an annular beam, so a beam that's hollow on the inside. And then that annular beam comes up through this window at the bottom right here, and then goes on up towards the sensor, although it doesn't reach the sensor. If a particle in this airflow here comes in and strikes the outside of this annular beam, we've got a situation that I'm showing over here, where it will scatter some of this light. That light goes up into a thick window. Here's the thick window. Now, most of it just goes through the window, but a small amount of it will strike the edge of the window where we've painted a reflective coating onto there. That then scatters light inside the glass, and a small portion of it will get trapped via total internal reflection. And eventually, some of it will sneak out of a hole, shown right here, that we've cut in the reflective coating that allows some of that light to leak out to a very sensitive PMT. So in this way, as the drone carries the instrument through the air, a particle can come in, hit this annular beam from any direction, and trigger the measurement. We've got a sequence of filters here that prevent the red trigger light from getting to the sensor. They also prevent ambient sunlight from saturating the sensor. Once we get a trigger signal from this red layout here, we then fire a green laser pulse that comes down and goes up again. So the green pulse is coming up this way towards the particle. It's a solid normal Gaussian beam, illuminates the particle. It does pass through all of the filters, and so we get the conventional single color or monochrome hologram with the red light in this case. Here's just showing you some pictures of the guts of HAPI. Here are the custom-made optical component holders and the Raspberry Pi and other custom electronics we use to control all of this, these steps. We call it HAPI's brain. Here's the team that built it. Osku Kempinen was the postdoc who led the construction and scientific study and proof of principle demonstrations with the HAPI. Here's the HAPI instrument itself, and then two undergraduates, Ryan Mersman and Jesse Lanning, who are helping him. And you can see it flying here on the drone. Here's a movie showing one of the early tests, obviously from the perspective of the drone. It's carrying HAPI up into the air. And now it's going to fly over to the spruce tree. And there's a good bit of wind. Obviously, you can see a lot of wind from the rotor, but there was also some wind normally that was causing pollen particles to come off of the tree, and some of them inevitably would go through the instrument, trigger it, and we would get some holograms. And this is just showing you an example of some data from that trial. Here's one of the digital holograms we got from that tree trial, if you will. If we reconstruct an image from this hologram, you can see very clear, large pollen particles showing up. And then if you compare them to the literature shown over here, of what these spruce pollen particles actually look like under a microscope, you can see, yeah, well, indeed, this kidney bean shape is typical of this pollen particle is certainly there. And so these most likely are indeed the spruce pollen spores coming off the tree. Here's one final example I'll show. Had one of my graduate students driving that Suburban down a dirt road at one of the research farms, instruments flying through the dust. And so we get a nice hologram of dust particles. We get many holograms indeed, but here's just one. And then notice when we reconstruct an image from them, we can get images at different focal depths. So for example, here, the Fresnel-Kirchhoff integral has been adjusted to produce a focused image of this particle. Down here, this particle. Down here, this particle. And all of this is coming from a single measurement. In other words, we don't have to repeat the measurements to bring particles at different locations into focus. And this is really one of the true practical merits of digital holography, is you basically get a whole lot of bang for your buck out of a single measurement. So perhaps to wrap things up here then, from a hologram, you can get aerosol particle size, shape, its angular light scattering pattern in 2 dimensions. I didn't discuss this, but you can also get a good estimate in most cases of the extinction cross-section of the particle from the hologram by performing an integral operation on the interference pattern directly. And then, of course, you can integrate the light scattering pattern, which in some cases gives you an approximation of the particle's light scattering cross-section. Of course, these are all important parameters we would like to know for atmospheric science studies and radiative forcing, climate, etc. So there's lots of potential here, and I hope I've given you a good idea of what we've done with this and what it can do. Quickly to acknowledge the team that made a lot of this work at Dr. Yuli Heinzen. She built up the holography and scattering pattern simultaneous measurement experiment. Also, Dr. Kempinen, who I already mentioned, led the HAPI team along with Ryan and Jesse. And then my current graduate students from Mesh and Claudia also contributed to the project in both experimental and computational aspects. Obviously, I'd like to thank funding, particularly NSF, Department of the Army, and more recently, Air Force Office of Scientific Research. Here's our website if you'd like to know more. All of our publications are published there for free. And with that, I thank you for your time, and please email me with any questions if you'd like.